Hello and welcome. Today we're going to be looking at Chapter 1, Section 2, Properties of Real Numbers. A couple of different objectives. We want to be able to graph and order real numbers and to be able to identify the properties of real numbers. We'll start by talking about the different subsets of the real numbers and how they are related. The set of real numbers is made up of two distinct sets of numbers, the irrational numbers and the rational numbers. So those two sets together make up all the real numbers. Every real number can be graphed as a point on the number line. We've got an example of 5 different numbers being graphed on the number line here, covering up several different groups. Here is some information about the different groups of the subsets of the real numbers. So starting with the natural numbers, we use the natural numbers to count. So natural numbers being 1, 2, 3, and then we use these 3 dots to show that we're going to go on forever using that same pattern. So those are the natural numbers. Whole numbers, the only difference between natural numbers and whole numbers is whole numbers include 0. So you can see we've got 0, 1, 2, and 3 in here. Integers are the natural numbers, their opposites, and 0. So we've got the whole numbers, natural numbers, 0, and we've got negatives as well. It gets a little bit trickier when we throw in rational numbers. Now, rational numbers include all of the integers, whole numbers, and natural numbers. See how that's set up here, how they're all contained within the rational numbers. But rational numbers also include numbers that can be written as a fraction or quotient of integers. We also have terminating decimals, like 6.1, repeating decimals, like 0.3 repeating. And so that includes all of those rational numbers. So again, those are numbers that can be written as a fraction, like a over b, where a and b are integers and b is not 0. Terminating decimals, so a fraction like 1/8 is 0.125, and that's exactly it. It stops there. And then fractions like 1/3, which are example of repeating decimals, that's what we'd put the line there for. So those are all rational numbers. Now we've got a distinct break between rational numbers and irrational numbers. So there's nothing that is both rational and irrational. So irrational numbers come from 2 main sources that we usually use, pi being one of them. So again, we know pi is a non-terminating, non-repeating decimal, so that's what makes it irrational. And then also when we take certain roots, specifically like the square root of 2 here, be careful though, not every square root is irrational. If you have a square root that works out nicely, like square root of 16, which is 4, then that is not irrational. Here we'll take a look at classifying a variable by determining which subset would be the best fit. In this case, your school sponsoring a charity race, which set of numbers best describes the number of people who participate in the race? Well, since the number of people can't be negative or a fraction, hopefully it's not 0, we would probably pick the natural numbers to best describe the number of people that participate in the race. And then at the bottom here, if each participant made a donation of $15.50, which subset would best describe the amount of money raised? And there we're not sure if that'll end up being a integer or not, or I suppose even a natural number, more precisely, or it could be rational, because if depending on if it's an odd number of donors, then we're going to get that 50 cents there, and that'll make a difference whether it's a natural number or rational. So we would really have to pick rational because of the possibility that it may not be natural. So rational would be the best choice for the amount of money raised. Here we're taking a look at just graphing numbers on a number line. So looking at negative 5 halves, again, you might think of that as negative 2 1/2 or negative 2.5, so right between negative 3 and 2. Square root of 2, again on a calculator, it's approximately 1.4, and that's about as accurate as we can really get with graphing a point on a number line. And 2.6 repeating, again, maybe help to think of that as 2 2/3, or just a little bit to the right of 2 1/2. Now if we make a number line for our points down here, starting with that number line, and let's see, we do have some positives and some negatives, so if I put 0 here, 1, 2, 3, just to cover everything that I need to, negative 1, negative 2, negative 3 there as well. If we approximate the square root of 3, that's approximately 1.7. So that would give me an idea of about where to put that dot for that. So square root of 3, it's about there. The negative 1.4 repeating, so again, just thinking of that as that repeating decimal. It's not quite the same as negative 1.5. It's a little bit to the right of negative 1.5. And then 1/3. So 1/3, again, just trying to put that between 0 and 1 in the appropriate place to get 1/3 for that. When comparing radicals like the square root of 17 and 3.8, one thing I do want to avoid having you do is just type in the square root of 17 into the calculator. What I would prefer to look at is the fact that the square root of 17 would be between the square root of 16 and the square root of 25. So I know that the square root of 17 is between 4 and 5. So without having to use a calculator, I can tell that square root of 17 is between 4 and 5, and I can actually tell pretty, or even closer there, that it's going to be quite a bit closer to 4 than to 5. But still, it's over 4, which 3.8 is less than. So the square root of 17 would be greater than the 3.8. If you wanted to, you could write that as 3.8 is less than the square root of 17. We do the same thing for the square root of 26 and 6.25. So the square root of 26 would be greater than the square root of 25, less than the square root of 36. So that puts that between 5 and 6, and again I can tell it's actually closer to 5 than to 6, so certainly the square root of 26 would be less than the 6.25. And then a little kind of problem for you to think about there with A, B, and C being real numbers where A is less than B and B is less than C. How would you be able to compare A and C? So hopefully you can figure that out. So looking at the properties of real numbers, so these are properties that are true for the relationships for all real numbers, except in one case we have to eliminate 0. When we talk about the additive identity for real numbers, we're talking about 0. 0 is the one real number that has no multiplicative inverse. So other than that, though, every other number will have a multiplicative inverse. Sometimes, usually we just call these opposites. Fancier term for it is additive inverses. So any number A and the opposite of A are additive inverses, and the sum for additive inverses is 0. And 0 is referred to as the additive identity. You can add 0 to anything and it doesn't change the value, so that's why it gets that name. Reciprocal or multiplicative inverse, so typically we just call it reciprocal, but the reciprocal or multiplicative inverse of any non-zero number A is 1 over A. Product of a number and its reciprocal is 1, so 1 is called the multiplicative identity. Again, if you multiply something by 1, you know that the value does not change. So here is a list of those properties. One that we don't use a lot, but it's kind of important, is the closure property. So the set of real numbers is closed for addition and for multiplication. meaning that if you take any two real numbers and add them together, the result has to be another real number. Likewise with multiplication, you take any two real numbers, multiply them together, and the result has to be a real number. Both addition and multiplication are commutative, meaning that you can rearrange your terms. So like a plus b is the same as b plus a. A times b is the same as b times a. So those are both commutative. They both are associative as well, meaning if we have a plus b in parentheses and we add c, then we can reassociate that, and we can put b plus c together first and then add a to that sum, and we get the same result. Likewise, same thing works with multiplication. Talked a little bit about the identity. So 0 is the additive identity. We add 0 to something and it doesn't change the value. 1 is the multiplicative identity, meaning we multiply something by 1 and that does not change the value. Inverse or opposites, add a number to its opposite, you get 0, and the reciprocal or multiplicative inverse, multiply something by its reciprocal and the result is 1. And then we also have the distributive property. Now, we do just call this the distributive property. More specifically, though, it is the distributive property of multiplication over addition or subtraction. There are other distributive properties, but this is the one we deal with the most. So looking at problems like this, we should be able to determine which property is being illustrated. So in the first example, multiplying negative 2/3 by negative 3/2 to get a result of 1, that would be our reciprocal property, otherwise known as the multiplicative inverse. And example B, notice how they reorder the 3 and the 4. So reordering things, that's the commutative property. Sometimes people get confused with that one because it has the parentheses in there. And again, that's done intentionally to make you have to think about it. But it's not associative, it is commutative because we're just rearranging the 3 and the 4. And then the problem at the bottom, we've got the 3 multiplying the g plus h quantity and adding another 2g at the end, and then on the other side the 3 has been distributed into those parentheses. So that is an example of the distributive property. Well, thank you for watching. Hopefully this helped answer any questions you have.